So I am going to talk about the geomorphic analog design method and how we can use geomorphic analog design to create a road stream crossing. Give you an outline of where we're going today. We're going to talk about the evolution of design approaches that have been used over the years at road stream crossings. Sediment transport and floodplain connectivity. I've already heard a lot about floodplain connectivity, but we're going to keep hammering that home. The culvert design process. And I'm going to touch on fords and bridges. And then finally, I'll give you an overview of geomorphic guidelines in Alaska. I want to acknowledge that this presentation uses materials originally developed by Bill Rice and Jillian O'Doherty. And I also want to thank them for their 15 to 20 years of work that really went into helping to build the foundation for where we are today with installing culverts for geomorphic function or stream function and ecological function in Alaska. So this slide depicts several different approaches that we might take to construct a stream crossing for a road or a trail. Depending on how the crossing is constructed, the crossing will provide for different functions and a range of ecological connectivity. At the bottom in detail E, you will see a traditional culvert that is just designed to pass a flood flow. At the top in detail A, we have a bridge that spans the floodplain and has little to no negative impacts on aquatic and riparian connectivity. It would be great if we could afford to put a full valley spanning bridge at every crossing, but we can't. So in order to be able to cost effectively construct most crossings, we end up here in the middle. The approach shown in these panels will help us to address the ecological function of passing fish and other aquatic species, especially in panels B and C, and providing for appropriate sediment transport and terrestrial animal passage. All of these things are the stream functions that we heard about yesterday. I will start by talking about all these methods today, but I'm going to start by working from the bottom and going up. So basically the lowest connectivity and function, which is a culvert that is just designed to pass the flood flow. Here's a couple examples of culverts designed just to pass the flood flow. And as Matt mentioned, this typically causes degradation downstream. Usually these are not installed at a lower flood elevation, or they're usually installed at grade, and these perches develop over time. And once they become perched, then they become barriers, of course. And then we've got culvert batteries. These are multiple culverts that are installed at the same elevation. And they are a problem because at low flows, they split the flow into multiple cells. So you add all those culverts up, they may equal the full channel width, but at low flows, we've got, we're not mimicking the natural channel low flow geometry, and we've got really shallow flow in all of these culverts, which is a problem for adult fish passage. So we started to understand these problems, and about 35 years ago, engineers and biologists teamed up to solve the problem. They came up with this laboratory method of measuring fish swimming abilities and some software to compare those abilities to the velocity in the culvert. Fish Pass is one of the versions of that software that was developed about 1991. Another version of software where we can look at the ability of fish to swim through a culvert and compare that to our hydrologic flood predictions is Fish Crossing. This software contains swim speeds for a selection of fish species, life stages, sizes, and water temperatures. Actually, it's interesting to note that The ability of fish to swim is different at different water temperatures. I believe they will not be as strong as swimmers when the water gets warmer. We know, the problem is that we know that different populations or stocks of salmon have different genetic characteristics and swimming abilities depending on their natal streams. And we don't have all of that data for all these different stocks. Also, researchers have noted there is a wide range in swimming speeds that affect, a wide range in swimming speeds that individuals display, even when the major factors affecting speeds such as species, size, life stage, and stock are taken into account. Differences in swimming ability may be due to physiological differences, e.g. the couch potato fish versus the track star fish. They also may be due to different levels of motivation and stress. I personally always run faster when I'm being chased by a bear. The bottom line is using fish swimming speeds that are determined in a lab under unnatural conditions. It's probably not a great way to predict if a life stage and species of fish will be able to pass through a culvert. And we also heard from Franklin's presentation that regression equations can have large degrees of inaccuracy. So this introduces another layer of error to this type of analysis. As this uncertainty extends to the high and low fish passage flows that we use for this type of analysis. The bottom line is fish crossing and fish pass probably don't accurately reflect how passable a culvert will be in the real world. And the result of these hydraulic design methods are structures that look like this: fish ladders and baffles. These structures disrupt the ecological stream process, and they do not work for all life stages or all species. Some species can't jump at all. Juvenile salmon can only jump 4 inches. So hydraulic design for a specific species did not work out as intended, and we started to look at trying to simulate nature. And the stream simulation method says that we want fish passage, sediment transport, flood, and debris conveyance within the culvert to function as they would in a natural channel. Early attempts, though, did not mimic the natural channel bankfold geometry. So I call this the non-geomorphic stream simulation method. Basically, we just put some rocks in a culvert. We might have put in sediment recruitment sills, which you see here, to recruit more sediment when the rocks are washed out of the floods and a higher flood flow. These usually don't work. The culverts are sized based on active channel width or the ordinary high water width and our design flood. So they are usually not as big as the bankfold channel width. And we are not using bankfold geometry or geomorphic principles. You can see for this culvert, the result was that all this substrate that used to be inside the culvert was washed out and is now disrupting the channel geomorphology downstream. So good intentions are not the whole story. You must also pay attention, and by pay attention, we mean pay attention to what the channel geomorphology is trying to tell you. Many guidelines and criteria don't really use geomorphic design principles. Here's one that does. This culvert that you see on the right was designed using the U.S. Forest Service guidelines for stream simulation, and these are geomorphic design guidelines. This culvert survived the 2012 100-year flood, and the picture was taken in 2020. So we see that the banks have remained in this culvert, and we still have a low flow channel and a nice water is staying on the surface of this channel, which is what we want to see. The U.S. Fish and Wildlife Service has recently developed these guidelines that are based on the U.S. Forest Service Geomorphic and Upstream simulation guidelines with some specifics for Alaska. These guidelines are written to address some of the stream corridor functions that we learned about yesterday. And those are, we would like to see a dynamically stable channel geometry. We want sediment transport to be in equilibrium. So that means sediment upstream and downstream of the culvert is going to move about the same as it does within the culvert. We want natural substrate in the pipe. We want woody debris transport. So we're moving that woody debris downstream to where it can help to create habitat. We want nutrient transport, aquatic organism passage for all species at all flow stages, terrestrial wildlife passage, and floodplain and riparian connectivity. And we want to provide for the 100-year flood capacity. We've had, this is definitely a concern about how much flood capacity do we need. Currently, state guidelines on state highways for culverts, there are 50-year flood capacity. So this 100-year flood capacity is higher than what folks are typically using or have been using in the past. Should we be using a higher flood capacity? Maybe. Can we afford it? I guess that's the question for each project, is to look at your project and see if you can afford it. Certainly, the higher your flood capacity is, the better. And I want to mention about these guidelines that we consider these a living document, and we plan to update them as we monitor and learn from the culverts that we are restoring using these guidelines. So we know that the goal of increasing stream function means that we must pay attention to geomorphology and floodplain connectivity. That means we're going to be in these panel B and panel C. We're going to pass sediment, debris, and all aquatic species. We're going to provide for floodplain connectivity where possible, and terrestrial animal passage where possible. This is just a picture of a culvert with a floodplain culvert to kind of give you an idea of where we're going. You can see that the natural channel is continuing through this culvert. This culvert is bank full width, and it was, this is a couple years after installation. Here's another one that went through the 2012 year flood. The bank materials made it through that. In fact, we're even seeing some deposition on the banks, which we'll talk a little bit more about later. But Matt mentioned yesterday that once the flows leave that bankful channel, we should be seeing deposition on our banks. However, inside of culvert, we are still constricting those flows. So we do need to use large stable material for our banks in the culvert. And I like this picture because you can actually see the grain sizes of the substrate in the low flow channel. You can see that the low flow channel has been maintained. So we're really achieving that dynamically stable geometry in this picture. Our primary goal is to maintain the stream geometry inside of a culvert. The study of geomorphology tells us that slope, precipitation, sediment, supply, and geology are the primary inputs that control stream geometry. And I think Matt did a really great job yesterday of explaining channel types and how they differ across the landscapes. I'm not going to get into that in detail. We do know there is such a strong correlation between climate, geology, and bankful geometry that we are able to create regional curves that reliably predict the bankful area, the bankful width, and the bankful depth for a given drainage area. The R-squared values are very good for these predictions. You'll see in these two, we've got an R squared of 0.91 and 0.96 for the width and depth, where the mean depth seems to be more reliable. And that area was an R squared of about 0.96 as well. So anyway, this tells us that channel geomorphology is a better predictor of the bankable discharge than hydrology estimates. And that's the discussion that Franklin and I were having a little bit at the end of his talk. Understanding and designing stream crossings for bankable geometry is the key element of a successful stream crossing. If we design for the bankable channel geometry, we are setting a road crossing up to work with the forces of nature instead of fighting against them. We know that the bankable geometry is driven by the climate and geology of an area. The bankable channel dimensions are also the primary drivers of sediment transport in a natural stream channel. The reason for that is once a channel spills onto the floodplain, roughness increases, velocities decrease. So out in here, we're getting higher roughness and we're getting lower velocities, and the larger sediments drop out, as Matt explained in his presentation yesterday. Before we get into crossing design, let's dive a little deeper into sediment transport. At equilibrium, Lane's balance tells us that slope and flow balance the size and quantity of sediment particles the stream moves. Except there's a little bit more to this story. So I'm going to give you a warning to pay attention to this. We're going to have a quiz on this soon. The setup here is we have a blob of water with dimensions, depth, width, and length. So with those dimensions and the unit weight, we can calculate the weight of our blob. And now we're going to apply Newton's law. An object in motion tends to stay in motion, which means if the flow is uniform and steady, all of the forces on our blob of water must add up to zero. This allows us to draw what physics types call a free body diagram for our blob of water, where we examine all the forces and make sure they add up to zero. So the vector component of the weight of our blob of water that is moving down the slope is offset by the drag force here on our stream bed. We know that these two forces acting on our blob of water must add up to zero if we have uniform steady flow. So we are not accelerating this blob of water, it's just steadily moving. We do a little math and discover that the shear stress experienced by the stream bed is directly proportional to the weight of the water times the depth of the flow times the slope. So, and shear stress is the force per unit area. So in our equations, these width and length functions drop out, and we're just left with the weight of the water, which is represented by gamma, the depth of the flow, and the slope that is driving the shear stress. So for a constant slope, really the only variable here is our depth of water. This analysis tells us that the shear stress increases with depth. So the deeper the flow, the higher the shear stress. So just put that another way, the shear stress, which is the force exerted on the channel bottom, is higher at deeper flows. This is because the weight of the water is more at deeper flows. You might have learned this from wading a stream. You want to always look for the shallowest part of the channel to make it easy to cross. You wouldn't go crossing in a narrow, deep section. And a word on slope here. So that sine alpha in this equation represents the slope. So if we have a steeper slope, we are going to have higher shear stresses. And that we often talk about velocity. So we equate that to higher velocities when we have a steeper slope when it comes to shear stress. So now I've got a little quiz, and Debbie, if you could go ahead and throw the poll up.
Yes. I'm launching the poll. So everyone's going to see a poll up on your, and you might have to move it out of the way. I believe everyone has that option depending on what your screen configuration is, but you should see the poll. There's 2 questions, both for this slide.
So yeah, I'll give you a little time to answer those questions. And I want to point out that the slide or channel A, we've got a wider channel, we've got the same bankful area, but our mean depth here is 19 inches. And in channel B, we've got a narrower channel, same bankful area, and a deeper depth. So based on what we just talked about, will the sediment transport in these 2 channels be the same? And which channel do you think will move more sediment? And I'll give you just a minute to think about that. This is a test of how many people are actually not multitasking.
Looks like we've got about 50 people who have answered so far. I can't see any poll. Okay. Good question. It should have popped up. If you can't see it, go ahead and you have a tool. If you wiggle your mouse, there is a poll option down below, and see if you click on it, if it will bring it up in your screen. What happens, I think, depending on how many screens you have, it might have gone to another screen. So see if that helps you. And it should say poll number 1, and there's 2 questions on it. We're up to 67. Did that help? Did those instructions make sense to folks? I'll look at the chat. Yeah, we're great. So now we're up to almost 70 folks. Yep.
I think we can keep moving on.
Okay, so we can end the poll. We'll end the poll and I can share the results. We'll share the results. All right. Are you seeing that, Heather? It should show you what the results are.
Yeah, I see it. Do you see it, Debbie? Or is everybody seeing that?
Yeah. Andy, are you guys seeing that okay on your screen? And again, I apologize if it's not popping up on your screen. Sometimes if you have multiple screens, Zoom will send it often to another screen. So it might be a setup for you, for each individual. And again, clicking on that poll box might help.
Okay, so yeah, most people got this right. Almost everybody got question number 1 right. So yeah, absolutely, the sediment transport is not going to be the same in these 2 channels. More sediment is going to move in channel B because the shear stress is going to be higher because we have deeper water. So the flows up to bankful stage have been shown to be responsible for forming and maintaining the channel features and transporting the majority of sediment in alluvial systems. So if we, this relationship between depth and shear stress helps us understand why that we just talked about. We also, I want to note that we define the bankful mean depth as the bankful area divided by the bankful width. So this is not the max depth of the channel, but we're taking the whole area and dividing it by the width of the channel. And when you get this over a widened channel, that's the reason why that mean depth goes down. And geometrically that works out. You can take my word for it, or you can do a little math. But by maintaining the hydraulic geometry, it flows up to the bankful stage. basically we can maintain sediment transport in equilibrium between the crossing and the natural channel. So we don't want to, you know, I think as engineers, we often want to like design a bigger channel, convey more water, but that decision actually has an impact on sediment transport and can cause problems. So we've got our next poll. And Debbie, if you want to go ahead and launch that poll. So the question for this is, which cross-section will better maintain a low flow channel? So this is the same cross-section. We've got the same bankful area. This wider channel is not as deep. The bankful area at the lower channel is the same, but it's deeper. But with our low flow channel, which is represented here, we have the same area in both of these channels. And the depth is about the same. This section A is actually deeper. So which cross section do you think will better maintain the low flow channel? I'll give you a minute. All right, let's go ahead and end the poll.
Okay, great. Ending the poll, and I'm going to share results. You should see results there.
So yeah, the majority of the folks got this right as well. That cross-section B is going to better maintain the low flow channel because cross-section A is over widened and we're going to expect aggradation to happen. So even though this aggradation may not happen at the low flow, because the low flow area looks fine, the sediment transport that happens up to the bankful discharge, and that's where the majority of sediment transport happens, is going to cause this channel to aggrade. So what does this mean for our goals of keeping sediment transport in equilibrium? How do we need to factor this into our design? I've got an example here of a culvert and channel that were constructed at 1.5 times the bankful width. And this was not on purpose. This was a contractor error. But we know that channels are over wide will result in aggradation, and over wide culverts also result in aggradation if the bankful channel shape is lost inside the culvert. We also had icing issues at this culvert. So this culvert was originally constructed with banks inside, I believe, and it was just the channel upstream and downstream. The banks were put in the wrong location. They weren't tied into the culvert correctly. So we ended up with this over wide channel. And that contributed to this culvert degrading. However, whenever we've got a culvert that's too wide or very wide, we have that risk of aggradation issues. And so we're recommending that we keep the culvert width between 1.0 and 1.4 times the bankful width. Now let's look at floodplain connectivity and that sediment transport process. The floodplain processes are not the same as the channel processes. We are looking now at flood flows that are greater than bankful or greater than the 1 to 2 year flood flow event. So channel A represents a channel that has been confined between a levee and a road. The cross-sectional area in the little yellow box here shows the flood flow that might go through at a 100-year flood. Hopefully not, because it's going to get that car all wet. But anyway, channel B is a system where the bankful channel has been appropriately sized, and we have connectivity to our floodplain. So flows are allowed to spread across the floodplain. So in section A, we're going to have erosive processes. The deeper flood flows will have higher shear stresses and will lead to excess bank erosion, channel incision, and degradation, and eventually Rosgan type F and G channels. Channel armoring is going to be required to prevent bank erosion and failure of that road. In section B, if we size the bankful channel correctly, the flows will spread out into this greater area into this floodplain area when they're over the 1 to 2 year flood event or over the bankful discharge. They're going to slow down and deposit their sediments, and we're going to have depositional processes in the floodplain. So basically, moral of the story is life is easier if we don't fight with Mother Nature. I think this is a little great graphic that shows the benefits of connectivity between the channel and the floodplain. We're keeping our floodplain wet and allowing for more biodiversity in the floodplain, both with the vegetation and with the species that are going to be able to live in that area. We're keeping the groundwater connected to the floodplain and able to supply those cool temperatures to our channel habitat. And our connectivity to the floodplain is also going to provide off-channel habitat and connections to wetlands for juvenile salmon, which is especially important during flood flows, but it's also a great place for them to go and hide from the predators like pike that like to hang out in those deeper waters. So we're going to start, move on to the design process. And the first step in the design process would be our assessment and feasibility, our hydrologic predictions, which Franklin has covered. I'm not going to cover that. We're going to set goals at our crossing site by looking at the crossing alignment and profile. Then we're going to select a reference reach, survey, and classify it. And this reference reach needs to be appropriate for our crossing goals that we just set. We're going to find a reference cross section from our reference reach. And if this reference reach is not adjacent to our crossing, we might need to adjust it for the watershed area. And we're going to select the structure size using geomorphology and hydrology to meet those bankful discharge or bankful channel widths and the hydrology to make sure that we have the conveyance that we need at the higher flood flows. And then we're going to design the substrate that we're going to put inside our culvert. And I'm going to go through all of that. So the site assessment, we need to know where we are in this watershed. Talked about the different channel types in the watershed. We definitely want to know what channel types we're looking at, where we are, and what our sediment supply is. And for channel types, if we're in a braided system, a D-type system, we want to consider, or we do want to have a bridge there. Very difficult to deal with those D channel types with a culvert, at least the actively moving braided systems. The anastomizing systems, we can potentially deal with those with culverts. We also need to consider channel instability. And we just need to be aware if we have it. The guidelines state that culvert crossings and systems that are actively degrading such as Rosgan FRG channels should be avoided. If they can't be avoided, they need to be stabilized on a reach length basis to prevent head cut or excessive lateral movement prior to the construction of a new crossing structure. I am not going to discuss how to stabilize channels, but there's some great courses if you need any recommendations on doing that. So existing crossing profiles. If your culvert is sitting on a uniform slope, this is ideal and it's easy to decide. This would be the uniform slope, what the crossing profile should be. However, roads are often located on the landscape at the toe of a slope or where there's a natural bench. This slide shows 4 examples of different longitudinal profiles: a uniform, concave, convex, and complex profile, which is a combination of the concave, and convex. Okay, this is like a tongue twister. So the concave profile is found where roads are located, where their steeper side slope meets the valley's forward. These areas are natural sediment deposition zone. The crossing that constricts the stream will exacerbate the natural tendency towards sediment deposition. Even where no constriction exists, natural aggradation can reduce a structure's hydraulic capacity. At our convex profile, the channel gradient steepens downstream of a crossing. So traditional culverts at these locations often control stream bed elevations. The risk of head cutting after the removal of our undersized culvert exists and depends on the stability of existing grade controls. So we have some solutions to these different profiles that we might find. And the solutions are to find a compromise between the 2 slopes that will keep the sediment moving and to provide stable grade controls where needed to prevent a head cut from traveling upstream and causing the culvert to become perched. And of course, our uniform culvert or uniform slope and uniform profile makes our jobs easier. So we also need to understand if we have local scour, which may be causing degradation downstream of the culvert, or if we have regional incision, where there's something going on that the channel is incising on a larger scale. If we have regional incision or local scour, our solutions are going to be different. So this green line shows the solution that we might have for local scour, and this green line shows the solution that we might have for regional incision. And the U.S. Forest Service has a great, in their manual, a little series of different ways that you might handle regional incision. So I would really recommend checking that out. So we're going to do a longitudinal profile at our crossing and determine what our target slope is at the crossing. And what we're looking for is trying to find the natural stream slope at that crossing. So that's this red dashed line. We've alluded to this, but this undersized culvert often traps sediment upstream and causes incision on the downstream side. So we need to make sure that we extend our survey far enough upstream and downstream of the culvert that we're getting outside of the impacts and of any of this undersized culvert or the road. So our best solution is to put our culvert at the natural stream slope and remove the trapped sediment. Channel reconstruction may be required whenever we remove this trapped sediment. But we might be in the situation where we are at a lake outlet with recreational uses upstream that need to be maintained. People might have docks or floatplanes or whatever. In Alaska, it's pretty common. And then we're going to need a steeper crossing, which means we're going to need a steeper geomorphic analog to design that crossing. Looking at the horizontal alignment here, if we've got a situation where the channel is crossing the road at an angle, it's best to either skew the culvert or do some kind of situation here where we've got head walls and letting the skew of the channel continue. Realigning the channel while possible, you're getting into creating a really tight curve here, which may cause erosion issues at the upstream side of your culvert. And it's just a curve that Mother Nature doesn't like because it's too tight. When we look at our horizontal alignment, we also want to avoid cutting off bends in a channel. If you cut off a bend, we're going to decrease the length, which is going to increase the channel slope. So we definitely want to try to avoid that. So Debbie, we're on to poll number 3. If you want to go ahead and cue that.
I will do that. Alrighty, so this is called new poll 3 here. It's launching. Folks should see this poll popping up. And there are 3 options. Which alignment will you choose? A, B, or C? And again, if you're not seeing the poll, it might have moved to a different screen. If you have like 3 monitors or something like that, go ahead and look in your other screens. You might see it there. Had about 60 people responding already. We're about 75 folks.
All right, let's go ahead and end that poll.
Okay, and then we'll share results. Folks should be able to see the sharing there. Looks like most people pick C.
So yeah, great. C is definitely a good solution because we are avoiding cutting off the bend and we're putting our culvert on the straight section of this bend. If you were going to put a new road in here, you might try to avoid this bend altogether. So awesome. And a lot of times we'll see that culverts historically have been installed straight across the road because they wanted to put in the shortest length culvert, and then they created this unnatural bend upstream. In that case, if you're restoring a crossing like this, we would recommend that you try to go ahead and put that culvert on a skew and emulate the natural sinuosity that you see in your reference reach. So on to selecting our reference reach. We're going to select a reference reach that matches our goals that we set for slope. I think that's going to be our major predictor of what type of reference reach we're going to be looking for. We know that we want the crossing slope to be within 25% of the bankfull slope of the selected reference reach. So for example, this example, we've got a bankfull slope of 1%, and we want our reference reach to be 0.75, or we want our crossing design to be from 0.75 to 1.25%. So if we have a crossing where our target slope is 1.25%, this reference reach would be acceptable. We also want to select our riffle cross-section that's going to represent our bankfull cross-sectional area. We usually want to take that in the upper 1/3 of a riffle, and because that's kind of where the flow is most parallel, and we're going to find the shallowest depth and the most uniform flow. So the flow vectors are more parallel there. And then we usually take pool cross sections as well. Those need to be in the deepest point of the pool. This figure represents the reference riffle cross section that we are going to use for design and the data that we need to collect in order to mimic this cross section in our new geomorphic analog design crossing structure. So that data that we need includes the width at bankful, the bankful mean depth, the bankful area, and the low flow channel cross-sectional area. So here's the bankful area and here's the low flow channel area. We also need to verify this bankful geometry. It's quite easy to confuse an inner berm for the bankful surface, especially in larger channels. So we're going to use as many methods as we can to verify that geometry. Regional curves, when we get them in Alaska, will be one method that we might use. There are other ways to do that, and I'm going to talk about that more in the stream surveying section. And then, of course, we're going to classify our channel. So we're going to have take the data from our survey and classify the channel, and we'll also talk about that more in the stream surveying section. Just a reminder, here's the geomorphic channel classifications from Rosgan that we have elected to use. And yeah, everything, you know, all of the different data that you need to collect there. So selecting a reference reach that is not near your crossing location, maybe from a different watershed, what do you need to know about that? We want our bankful width to be, of our reference reach to be no less than a half or no more than 1.5 times the bankful width of our crossing. We want the discharge of our reference reach to also fall within 0.5 to 1.5 of the bankful discharge. And we want our stream order to be within 1 stream order of the crossing. And we want to be in a similar physiographic region and hydrologic regime. So these are big words, and I think it's worth reviewing the definitions of these. I know I like to look things up. And so the physiographic region is a region having a particular pattern of relief features or landforms that differ significantly from that of adjacent regions. And the hydrologic regime means the timing, volume, and duration of flow events throughout a defined period of time, which may be influenced by the climate, soils, geology, groundwater, watershed land cover, connectivity of the stream, riparian area and floodplain network, and valley and stream morphology. So a lot of those concepts that Franklin just covered. So how do we scale a reference reach? We're going to do this if we don't have a suitable reference reach upstream or downstream of our channel for any reason. Maybe it's the wrong slope, or maybe we don't have a single thread channel. I don't know if I mentioned that earlier, but we do need a single thread channel to be our reference cross section. So we're going to select that reference reach. Maybe it's going to be near another culvert. So we're going to make sure we get outside of the influence of that culvert. And we're going to survey the cross section of our reference reach. And then we're also going to survey a cross section at our design reach, assuming that we can find one. And we're going to calculate the discharge of each one of those cross sections, the bankful discharge. And then we can use these equations and the relative value of those bankful discharges to scale up our reference reach cross section and end up with a single thread cross section, or a single cross section that we can use in our new channel design. In the case where we maybe can't find a good cross section at our design reach, we might use the synthetic width method, and Bill is going to talk about that later, not today, tomorrow, maybe, or the next day, can't remember. So Another thing we need to consider is the vertical adjustment potential of our crossing, which is another way of saying what's the potential of scour potential. We need to look at our natural grade again. So that would be this green line. And remember that a lot of times we have sediment that has accumulated upstream. We also might see sediment downstream, in the case excess sediment downstream that has accumulated, and that tends to happen when we have road failures in rural Alaska, and we actually see this quite a bit. So getting into this a little deeper, we're going to measure the max pool depth in a natural pool outside of the zone of influence of our culvert. And then we're going to apply a factor of safety to that max pool depth, depending on what our boundary layer consists of, what our channel materials consist of. So finer materials are going to have a higher factor of safety. And that's going to be the scour potential that we would use if we use this method that the U.S. Forest Service developed for estimating a lower vertical adjustment potential line. You could also use other published scour methods to come up with this. For the upper VAP line, in this case, we just drew that through the accumulated sediment bellweg. And if you have debris flows, your upper VAP line, or potential for debris flows in steep headwater systems, for example, your upper VAP line would be at your bankful level. And then we're going to place our new culvert in this situation, and we want to make sure that the bottom of our culvert is below that lower VAP line that we just established. And we want to make sure that if we do have aggradation, whatever line we consider there, we've got enough hydraulic capacity in our culvert. So we're just designing for the worst case scenario here. For woody debris transport, we want to think about the headwater depth of our culvert. So because the culvert constricts the flood flows, we're going to see the headwater raise upstream of our culvert at higher flood levels. So the headwater is going to get higher than what it's going to be in the floodplain, and we want our headwater depth ratio to be less than 1, ideally 0.8, so that we've got room for that woody debris to get through our structure. And I'm just going to page to this slide because I think this is a little more clear. You can see that there's some headspace at our 100-year flood flow and room for woody debris. So there are various approaches to providing for stream function. This is one of them, a bankful with culvert plus floodplain culverts. We are going to keep our low flow channel in this culvert, and we're going to design substrate that's stable to the 50-year flood. The culvert walls simulate the stream banks. And the floodplain culverts allow for some floodplain connectivity. And here's an example of that. So, and another example of a floodplain culvert. So that floodplain culvert is higher than our primary culvert, and we only have flows going through it at flows higher than bankful, or at least higher than the low flow channel. And we've got some guidance in the design guidelines on this that I'm not going to go through in super detail, but I just want to refer you to those. These are figure 4, so you can take a look at that. And you, if there's a side channel that's naturally established, I would consider placing your floodplain culvert to intercept that as possible to try to maintain those processes in the floodplain. We also might have a culvert with stream banks inside, These stream banks need to be designed to be stable to the 100-year flood so that they will persist. They provide additional roughness for slowing down the water. So that's great. Pit tag studies have actually showed that juvenile passage increased once flood flows overtop these banks because the juveniles were able to use the slower, shallower water and the roughness in the banks. So that's pretty cool. It really emulates what would happen in a natural stream where juveniles would use the floodplain habitat to escape high velocities. Here's a culvert that was constructed with stream banks inside of it. We were maintaining our low flow channel and we're maintaining that flow on the surface because we have a well-graded substrate. We're going to talk more about that soon. Another culvert with stream banks inside, really large rock needed in this very large culvert in Tyonek. But we can see the natural substrates are still moving through this culvert, the finer substrates, and moving through the bankful channel dimensions. We want to make sure that we connect or that we reconstruct our channel outside of the culvert as well. And we want to mimic those dimensions inside and outside and tie those in together. So in the plan view, we've got our channel outside our culvert. The channel lines are shown here in red, tying in to the channel inside the culvert. So there's no discontinuity there. We might also install a bank full width culvert. So this is the minimum culvert width for a geomorphic design in order to maintain those bank full hydraulic dimensions that we talked about. And this helps us maintain sediment transport continuity as well as we've also talked about. And this is an example of a bank full channel that was constructed in Kodiak. And you can see that these, the natural channel has been reconstructed outside. We've got some bankful benches here, and the culvert walls are acting as banks. Here's another bankful with culvert. The low flows stay on the surface, or are staying on the surface in this culvert, which is great. This picture was taken in 2019, a year after this culvert was constructed. And as you know, 2019 was a drought year, super dry conditions, lots of streams going dry all over the place. And yet we were able to maintain connectivity through this culvert. We also might install a culvert with banks inside and floodplain culverts. And I think this would be the highest level of stream function that we might get with a culvert. And open bottom culverts are another option. And they're a great option because they do allow for some groundwater connectivity, but we have to make sure that we protect those footings in an open bottom culvert as they're more susceptible to scour. Moving on, bridges are another great way to cross streams. And if we construct a bridge, we'd like to see them at least bankful width or greater. If they're greater than bankful width, we're providing for a terrestrial animal passage along those banks, which is a bonus. And we're allowing for those depositional processes to happen because those flood flows are spreading out and slowing down and dropping out their sediments. So that's great for maintaining the vegetation, but it's also great for protecting your abutments on your bridge and your bridge foundations, because you're just not going to see that scour process. You're going to see a depositional process. And here's an example of a bridge that is greater than bankful width along the Alaska Pipeline Road. And you can see that we've got some bankful benches. This isn't the best angle, but bridges can also be installed, and we see this all the time, that are less than bankful width. They maybe fill the floodplain and put in abutments in order to reduce the bridge span and come up with a cheaper bridge. So these bridges are going to affect channel and function and stream function just as much as an undersized culvert width would. So we would not want to see bridges installed that are less than bankful width. This 60-foot bridge in Indiana was plugged by debris during a flood, mainly by branches and corn stalks. So even bridges can be susceptible to this. A local farmer unplugged it using a backhoe. We got to watch out for undersized bridges. And I think this bridge is probably less than bankful width. You can see the, the bank, top of bank here seems to be up here, and yeah, so I think a good example of where, if they provided a little more capacity, a little wider bridge, that they probably wouldn't have had this problem. And I want to mention that the Federal Highways definition of a bridge is anything over 20 feet. So just because it's called a bridge doesn't mean it's good. We still need to consider these geomorphic channel dimensions. Fords and low water crossings also need to consider geomorphic channel analog principles. Alaska Pipeline, I borrowed this photo from a presentation that was given by Jeff Street of Alaska Pipeline. They've done a really great job on their fords and have figured out how to install these so that they're maintaining the low flow channels and water in that low flow channel and preventing subsurface, the water from going subsurface. And they're using grade control structures basically downstream to backwater the crossing. Hopefully we can maybe get Jeff to come and talk about this more. So we've got another poll, and I wonder if maybe we should just skip this because I think I'm running short on time.
It's about 12:24, whatever you think.
Yeah, let's skip that, and I'm just going to tell you the answer. The best substrate gradation is C. We want to have a well-graded substrate with rock-to-rock contact. So we don't want to have a gap-graded substrate where we've got big rock and then a bunch of sand in there. Without rock-to-rock contact, especially, that's going to settle and the fines will wash out. Even if we have rock-to-rock contact, eventually these fines are going to wash out, and we're going to end up with diagram D here, loss of surface flows that may trap fish and definitely are not going to provide for connectivity. And here's an example of those loss of surface flows. And that happened at a culvert that was installed without a well-graded substrate. We see the water going into the substrate and then just exiting here. So substrate stability, there's a lot of different ways to design substrate for stability. And this is one method that we have developed using Federal Highways circular and US Army Corps of Engineers equations. This method designs a substrate for stability at the D30 particle size. So D30 is the size that 30% of the particles are going to be smaller than the D30. So that's a pretty conservative design as far as using the D30. Most stability analysis use the D50. But we want to also make sure that our substrate that we put in our culverts are well graded. The well graded substrate means that we're going to achieve maximum density, and that's going to help keep our water on the surface of our substrate. So when we're using riprap from the Alaska Department of Transportation specification, these are very uniformly graded materials. So we're going to have to mix different types of riprap to get a well-graded riprap. And then we're going to have to add fine material. And this spreadsheet just helps us combine all of those and will make sure that our combination, our gradation combination, matches the Fuller-Thompson equation, which is an equation, as I mentioned, to predict maximum density, which is going to equal minimum porosity. And here's a picture of a well-graded substrate being mixed on site. So we're mixing the riprap with the fines, and we usually do that on site before we put them into the culvert. And an example of this going into a culvert, so you can see this riprap is already mixed with the substrate, and this is what this culvert looks like at the end. This is the Boy Scout Lake outlet culvert in Kodiak. And they were able to, even though they've got some really large riprap in here, they were able to create a channel that really emulates the natural channel shape very well. We're going to think about constructability with our riprap sizes or our D100 size. I want to mention that you don't have to use riprap. We could also use rounded particles, which are also great if those are available. But our bank width needs to be at least 1.5 times the D100 to make this constructible and to make sure that we are able to get a well-graded substrate. So we've got room in there for our big particles and our medium-sized particles and our small particles. And the same goes with the embedment depth. We want to make sure that that's deep enough that we really have room to put our substrate in there. We also might consider using some finer material in our low flow channel that's going to allow for some natural scour processes to happen. So a word on scour pools. Scour pools typically happen downstream of undersized culverts, and they alter sediment transport, allow for increased predation opportunities, and increase the risk of the new culvert that we are putting into this location of becoming perched. They also increase water temperatures because it's a large pool area that is going to be more susceptible to warming. So we recommend that you reconstruct the channel and transplant native vegetation along the banks when you install your new corridor and basically fill this scour pool. It's okay to have smaller pools that emulate the natural pools in the channel. We just don't want to see these massive oversized scour pools. Phew, so I now want to do a little comparison of some guidelines. This is the these are federal guidelines that are available, and we've got the U.S. Fish and Wildlife Service guidelines, U.S. Forest Service, and NOAA, and the Federal Highways guidelines, and we look at the different recommendations and how they compare. This is in our culvert design guidelines. I want to note that the U.S. Fish and Wildlife, Forest Service, and NOAA guidelines all use the geomorphic design approach. The Federal Highways guideline, HEC 26, as it's known to a lot of you, has a lot of great info on geomorphology, but they ultimately do not use a geomorphic design approach. The design approach in this HEC 26 is based on hydrologic predictions and does not have any guidance on setting channel dimensions based on geomorphology. So it's not a geomorphic design approach. And using those hydrologic predictions, we're introducing a lot of potential error into this design. So we hope to see these guidelines updated in the near future. A little bit more about the differences between the guidelines. All four methods require a stability analysis. we are always constricting those higher flood flows, the flows above bank flow discharge when we install a culvert. So the velocities are going to increase, the water depth in our culvert is going to increase, and the shear stress on our substrate is going to increase. Under the U.S. Fish and Wildlife Service guidance, we first look at the upstream sediment supply. For streams with upstream sediment supply, we would like to see the sediment designed for a 50-year flood. For a 100-year flood, it should be used for streams that do not have this upstream sediment supply. The U.S. Forest Service stream simulation method, they basically do a sediment transport analysis and compare the mobility of the upstream sediment particle or supply at the D84 particle size to the mobility of the D84 particle size in our culvert. Basically, these guidelines tell you to increase the sediment size in the culvert to account for increased shear stresses that a culvert is going to experience compared to the natural channel, where the flood flows have more room to spread out. So in the natural channel, we are seeing, the flood flows can spread out. I think that a lot of people misinterpret this. Well, they will do a pebble count in their upstream reference reach and then use the same materials in the culvert. And that's not what these guidelines are telling you to do. They are telling you that you need to upsize your sediment to account for those higher velocities. We find it a little more straightforward in our guidelines. We just went with design for the 50-year flood or the 100-year flood, depending on your upstream sediment supply. And the Forest Service guidelines basically says if you don't have any upstream sediment supply, their method does not apply. So really understanding the mobility of that upstream sediment is important. I want to mention again, even with a stable substrate, we are going to still have those smaller particles moving through the bankful channel geometry in the culvert. So this substrate just provides a stable base layer to maintain that bankful channel geometry. And in order to maintain that bankful channel geometry, we want to make sure that our banks are stable, so they're designed for the 100-year flood, and any other forcing features that we're using to maintain, say, the low flow channel stability, which Bill's going to talk about in his presentation, are also designed for the 100-year flood. I also want to point out that with all of these design methods, a check of the culvert velocity versus the fish swimming ability is not required, because we are emulating the natural stream conditions.
I want to call out the Alaska-specific design guidelines that use geomorphic analog methods. Both the Mat-Su-Buro and the municipality of Anchorage have incorporated geomorphic design guidelines into their code. Here's where you can find copies of Alaska-specific geomorphic design guidelines online.